Okay, hello everyone. Welcome back to another Topos Institute Colloquium. Today we're very happy to have Aleks Kissinger telling us about the ZX calculus and fault-tolerant quantum computing. So please, Aleks, whenever you're ready.
Thanks. Thanks, David, and thanks for the invite for giving this talk. It's really nice to be here. I apologize in advance if there's any dog barking, so I'm giving this from my house. And also feel free to interrupt if you have questions throughout. As I get sort of toward the end, I might speed up a bit, but in any case, you can feel free there. So yeah, so I'm going to talk about some kind of give a bit of a kind of educational overview and a bit of a survey of what's been happening in between ZX calculus, which is a kind of a graphical compositional language for quantum computing, and fault-tolerant quantum computing, well, I'll say a bit more about what that means and why we need it soon. Um, Okay, so quantum computing, as many people I'm sure have heard, is all about quantum computers. So quantum computers encode data in quantum systems. So these are usually microscopic states of particles such as photons or ions. And this enables us to do computations in totally new ways. So it's not really accelerating normal computing. It's really just a totally different way of doing computing. And my area, I would say, of expertise is what I would call quantum software. So I spend all of my time thinking about the code that runs on quantum computers. So an example of that is a quantum circuit, which you can think of as basically the assembly language of quantum computing. So you can really see it as just a kind of a list of basic instructions, which a quantum computer knows how to do. So each of these instructions corresponds to some kind of physical operation. Say it's going to, put the system in a magnetic potential for a certain number of nanoseconds or that sort of thing. And these are kind of the analog to arithmetic gates that you could find or instructions that you could find in classical assembly language. And this area of quantum software, it's really not just about code, but also things that make that code better. So I spend a lot of time thinking about optimizing quantum circuits, also classical simulation verification of these things, and quantum error correction, which I'll talk about some more. Okay, so I want to start by giving a little bit of a flavor of what ZX calculus is like and what it's for. And I think a good place to start here is talking about kind of the old-fashioned way someone might think about optimizing a quantum circuit. Okay, so maybe a kind of 90s style quantum circuit optimization. As I look at this circuit and I just think about the kind of rules that I know about gates. Okay, so if you know a lot of things about quantum circuits, you might realize that if I have a pair of these things, which are called H gates, that I could just push them through this thing, which is called a controlled NOT gate, and the controlled NOT flips around. Okay, so that's just a basic rule which says that these two circuits behave the same as each other. And now when I have a pair of controlled NOT gates, they cancel each other out, and I end up with a circuit that's slightly optimized here. Okay, and this works, and you can start to come up with a lot of these rules. And then you can come up with some more, and then some more, and then some more, and then some more. And it's um, it's kind of hard to know when to stop with this. Okay, so circuits are pretty much an unstructured space and they're kind of rigid. So often you need many variations of the same rule to capture some idea that you might want to use for optimizing. Okay, and that's where the ZX calculus comes in. So the ZX calculus is a simple set of graphical rules. Okay, so now the generators of a computation are not these gates, but they're nodes. And these nodes are labeled by angles. And I'll say a bit more about what that means semantically soon. But the important thing is that this thing, rather than being rigid like a circuit is, this is basically an undirected graph. So when I apply these rules, I'm doing graph rewriting. And this is a very powerful way to work with circuits. So if I look at this example that I had before, I can take all of these gates and I can cut them open. And inside, you can see that they're spiders. Okay, so quantum circuits can quite readily be interpreted as these things, which are called ZX diagrams. And then this diagram, I can start to apply those graphical rules. So for instance, dots of the same color fused together, that's a very important rule. And various other rules, which once you get used to them are pretty easy to remember. So for instance, these one-legged red dots will copy through the many-legged green dots, and some more fusions, delete parallel edges, and so on. And using those rules, you can get to something that's a lot more that's much more simplified. Okay, so that's the basic idea. So you might want to start with a circuit, simplify it, and possibly extract a circuit back out. So extract a gate decomposition of a ZX diagram. There's a Python tool for doing this, which is quite popular. It's called Physics, pronounced like physics without the H. It's on GitHub. There's also a Rust port, which is designed for doing this kind of at scale, and particularly for the applications to classical simulation, which is very computationally intensive. The Rust port is quite useful. Another thing which is kind of fun is this program ZX Live, which is a GUI tool based on physics, where you can sort of drag and drop and do these kind of ZX rewrites. And something that I'll refer to a little bit throughout this talk is a new free book called Picturing Quantum Software, which you can also get on GitHub. So you can just go here and get the PDF. And also I put a link to these slides, so you can find all of these links in my slides. And there's this web page, which I'll refer to a couple of times as well, zxcalculus.com. The community lately has done quite a good job of keeping track of all of the papers and sort of tagging them and making it kind of easy to access. So there's a lot going on there as well. Okay, so the main thing that I wanted to talk about today, now that I'm kind of done with sort of generalities about ZX, is how ZX is related to quantum error correction. Oh, I see that there's something in the chat. Yeah. Thanks, David. David just posted the link to my slides in the chat. Um, yeah, I want to talk about quantum error correction. Okay, so quantum errors, what are these things? Well, in classical computing, if you were thinking about, say, applying a logic gate to some bits, and you wonder kind of what's the error rate on modern classical hardware, according to Google, this is something like 10 to the minus 18. Okay, so you can run a very, very long classical computation with many, 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 basic steps in your assembly language and just never expect to see an error because this is a very small number. Um, Comparing to the situation with quantum computing, the kind of state-of-the-art quantum hardware, the gate error rates are between 10 to the minus 2 and 10 to the minus 5. Okay, so that's pretty high. 10 to the minus 2 is saying that if I run 100 gates, the odds that my computation is garbage are actually very high. Okay, and there's a lot of reasons for this. So decoherence, your quantum systems kind of want to get entangled with stuff that you didn't intend to entangle them with. Thermal noise, crosstalk between magnetic and sort of electrical signals, cosmic rays, and all sorts of stuff. So here's an example. This is kind of small, but I pulled this off of IBM Quantum. This is one of their devices. I think it's Brisbane. And it's showing the sort of single qubit gate errors as 10 to the minus 4, and the 2-qubit gate errors as 10 to the minus, or 6 times 10 to the minus 3. So that's kind of typical for superconducting hardware at the moment. And another thing that I thought was kind of cute was I found this on Google Quantum AI's blog, which is what happens when a cosmic ray actually hits a quantum computer. So you can notice that these are kind of all the qubits in this computer, and when the cosmic ray hits it, they all just go berserk. Okay, so that basically ruins your computation. Anyway, this is all just to say that errors are a big problem in quantum computing. And the probability of a successful, interesting computation, if we're not correcting these errors, is essentially zero. Okay, so I think 5, 6 years ago, we sort of thought we might be able to get away without doing error correction and still do some interesting stuff. I think broadly the community is starting to move away from that idea and thinking, well, really to do something interesting, we need to be thinking about error correction now. Okay, so how does this work? Well, the basic idea or the kind of standard paradigm for quantum error correction is the following. I take some space of logical qubits. So a qubit is my kind of basic unit of quantum computation. So I take some space of k logical qubits and I embed that up into a bigger space of n physical qubits. Okay, so when I say space, you can really think of a complex vector space. Okay, so this is a space of size of dimension 2 to the k, and this is a space of dimension 2 to the n. And now E, this encoder map that I've drawn, or sometimes just the image of this map, is called a quantum error correcting code. Okay, so if you know anything about classical error correction, you realize one of the ways this gets formalized is as a subspace of the linear space of bit strings. This is kind of by analog to that. It's a subspace of now the complex linear space of qubits. And now the game of fault-tolerant quantum computing is to take an error correcting code like this and figure out how to encode and possibly decode logical states and quantum measurement outcomes from this physical space into the logical space. And in the meantime, measure the physical qubits to detect and correct errors. And then, so those first two things will give you an error-corrected quantum memory. Then if you want to actually do some computation, you need to figure out how to do computations directly on the physical qubits. So I have some logical computation I want to do. I need to figure out how to do it in an encoded way on the physical qubits. Okay, because it's not going to work to decode to logical qubits because then I'm susceptible to errors. Okay, so that's kind of the basic idea. Um, I I will, without going too deep into the kind of nitty-gritty of this, I'll try to fill in some of the details or at least give a flavor of how this works. Okay, and the way I'll do this is using ZX calculus. Okay, so rather than seeing it explained kind of in the way that it would be in a quantum computing textbook, we can mostly explain this just using ZX. Okay, so I will give you a little bit more detail about the ingredients. So ZX diagrams, as I said before, are made out of these nodes called spiders. So how is a spider interpreted? Well, this is interpreted as a certain kind of linear map. This is a matrix, so if it's got m legs in and n legs out, this is going to be a 2 to the n by 2 to the m, or 2 to the m by 2 to the n matrix. And it's got a 1 in the upper left corner, and it's got an e to the I alpha, which is this little alpha parameter here in the bottom right. Okay, so what is this thing? I mean, it just turns out that this is a very useful basic generator for lots of quantum operations. So we have this one, which is called the Z spider, which is drawn in green, or it's lighter for anyone who's colorblind. And then we've got the darker, or we've got the red spider, which is the same as the green spider up to a basis change. Okay, so all of these legs now get this basis changing map, which is called a Hadamard gate applied to all their legs. Okay, but it behaves exactly the same, just up to a change of basis. Okay, so these things can be used to construct basic pieces of quantum computation. Okay, so they're not physically meaningful by themselves, but they can be used to construct physically meaningful stuff. So the first thing, and this is kind of what they were originally intended for, is you can use them to construct quantum gates. Okay, so here we have a 2-qubit gate, which is called a controlled NOT gate. Here I've written just the H gate as this little yellow box. Could also write it as spiders if I like. These things are called phase gates. In Anyway, it's not too important, but what these things do is they actually do the computation. Okay, so I have a quantum state, and my quantum circuit consists of a list of gates, and these things evolve my state to something that I want to measure at the end. Now, quantum measurements are the thing that give me an answer at the end of a quantum circuit. And what these do is they collapse a quantum state into a fixed state, depending on the outcome. Okay, so these are two simple 1-qubit measurements. One of these is with respect to let's say red, and one of them is with respect to green. So these are two measurements with respect to two different bases. And I get so if I did this, so say I perform this measurement, I'll get an outcome k, which is a bit. So my device, which does this measurement, maybe it clicks or it doesn't. So it gives me a 0 or a 1. And if it gave me a 0, then this process happens. And if it gives me a 1, then this lower process happens. Okay, and this part that's been disconnected is really just a scalar factor, which tells me about the probability of these two branches occurring. But the thing to notice here is that, I started with some state psi, which could have been arbitrary, and then in the end, it collapses to one of these two fixed states. So when people talk about measuring a system collapsing the state, this is what they mean in quantum physics. Okay, and now I want to talk a little bit about errors. Maybe I should pause there briefly. Are there any questions about the things that I said so far?
Are you saying that when k equals 0, it means that the top one happened, or that when k equals 0, the next thing that your machine will do is the top one?
It means that the top thing happened. So you should
Happened.
really think of this as a non-deterministic process, which you say, do this non-deterministic thing, and then the machine will tell you which thing happened.
Mhm. Got it.
Um,
Thanks.
and and all quantum theory tells me is the probabilities of each of those branches occurring,
Right.
which is actually just going to be the absolute value squared of these numbers.
So you didn't give us a conditional if then here.
Yeah, it's not
Yeah,
it's it's
got
it's
it.
it's not a if then. I don't get to choose. I don't get to choose the outcome. Sort of nature chooses it for me.
Gotcha. Yeah.
Any other questions? Okay, I'll move on. So how can we model errors? Okay, this seems quite non-trivial. Quantum states are a much bigger space. How should we really think about an arbitrary error happening in my system? Um, so in classical error correction, so if you think about the kind of error correction that the internet uses, um, a very simple error model just assumes that at each time step or at each noisy transmission of bits, each bit might get flipped with some fixed small probability p. Okay, and then if these probabilities are small and if they're independent of each other, then classical error correction works. So we know how to do that. You can send some bits and you can also send some XORs of those bits, which are called parities. And that's enough information to correct errors in this kind of setting. This generalizes to the quantum case, but now there's different ways that a quantum system can flip. Okay, so if you picture a qubit, the state of a qubit is living on the surface of a sphere. Okay, so that's just really a way to imagine the geometry of a normalized 2D complex vector. But anyway, that's not too important. So if you just picture it as a sphere, um, then I can consider some basic flips, like an X flip, which is a 180-degree rotation or a pi rotation around the x-axis, and similarly for a Z flip and a Y flip. Okay, so a Y flip, Y is kind of a second-class citizen in ZX calculus. We can write it as a composition of the X flip and the Z flip there. Okay, so here we have kind of three different errors. And we want to try to correct these. Okay, so we imagine a kind of a simple error model where these are the only errors that can occur. But it turns out this is not too much of an assumption because these three errors plus the non-errors, so the identity, actually span the space of all operations that could have happened. Okay, so in many settings, it's suffices to just think about one of these errors as having been the thing that happened with some small probability. Okay, and for the purposes of this talk, if you think about errors that way, that will be perfectly fine. Okay, so one of the ZX rules is that if I have two dots of the same color and they come to get and they are adjacent, then I can fuse them together and their phases add together. So a consequence of this is if I have one of these errors, and it's before I do a measurement, then I can think about what happens if I try to push that error sort of through the measurement. And if you see what happens, so these two red dots will merge, and then I can sort of unmerge that error off the right side. And you can see that in the process of pushing this error through, I flipped the measurement outcome. Okay, so if it was 0 before, it's 1, and if it was 1 before, now it's 0. Okay, because k is changed to k, or k pi is changed to k plus 1 pi. Okay, so errors really cause errors. And you can think, well, what is the difference in these different kinds of errors? Well, they flip the measurement outcome of the same kind, right? So because I did a red measurement here, then a red error flipped my measurement outcome, which of course is a problem. Okay, so how are we going to detect these things? Well, we can try to detect errors with measurements. But single qubit measurements cause problems, right? And the reason for that is that they just totally collapse the state. Okay, so presumably I had some interesting data encoded in my quantum state. And if I do a measurement to try to detect errors, I'm just going to collapse my state. So I'm just going to lose that quantum data. Okay, so that's a problem. Um, but there's a way around this. And the way to get around this is rather than thinking about doing single qubit measurements, I can do multi-qubit measurements. Okay, so this 1 qubit measurement can be generalized to an n-legged version. And what this is doing, or the way to think about this measurement is it's a quantum parity check. Okay, so it's a quantum analog of taking the XOR of a bunch of bits and seeing if it's 0 or if it's 1. Or put another way, are there an odd number of ones or an even number of ones? Okay, so kind of more rigorously, what I mean by that is the n-qubit basis vectors are all labeled by bit strings. And if I get outcome 0, that projects me onto the subspace of all the even parity basis vectors. And if I get outcome 1, it projects me onto the subspace of all the odd parity. Okay, but importantly, these are no longer 1D subspaces. These are subspaces of big dimension. Okay, so I can still have some interesting quantum data in there and do these kinds of measurements without destroying it. And similarly, if I just flip the colors, this is like doing a parity check, but now rather than with respect to this red basis, it's with respect to this green basis. Okay, so these measurements and variations on them are kind of the bread and butter of error correction. Okay, so these things are called Pauli measurements, multi-qubit Pauli measurements. So I'll show you how this can work. Okay, so here's a very simple example, which is called the GHZ code for Greenberger, Horn-Zeilinger, the people who came up with the experiment that this kind of state was based on. So what does it do? I take a quantum state, a qubit state, and I encode it as 3 qubits. Okay, and what have I gained by doing that? Well, now, if I do one of these parity measurements on 2 of the legs, this is actually going to leave my state untouched. Okay, so I paid a price by encoding this thing in more physical qubits. But the benefit is now there's certain measurements that I can do on this state, which leave it invariant. Okay. This kind of measurement is called a stabilizer measurement. Okay, so in particular, this thing is called an eigenstate of this measurement, so it just passes through unchanged. So in the absence of errors, it doesn't do anything to my encoded state. Um, However, if I do have some errors, so in this case, say I had a error here, this is an xflip error on one of my physical qubits, it's actually going to flip my measurement outcome. Okay, so remember this k is like my measurement outcome. So if it was 0 before, it's going to be 1 now. Okay, so it will detect the presence of that error, but it will otherwise leave that state unchanged. Okay, so since in this case, I was able to detect that there was an error there, then if I have enough information, I might even be able to identify where that error was, and I can fix it. Okay, so this detection is called an error syndrome, and then trying to figure out where my errors are is called decoding an error from a syndrome. Um, I saw there was, that's just some reactions to the slides.
I had a
Um,
quick question.
sure.
This delta 1k is the like Kronecker delta of whether 1 equals k. And
Yeah,
so
yeah.
you're
So
getting either 0 or 1, and if it's 0, that means you just have 0 as your entire output.
yeah, so you can, like I said when I was talking about these measurements, the scalar that sort of gets kicked out from doing the measurement, that represents the probability of that branch occurring. So
Mhm.
in this case, where no error happened, the probability is delta 0k. So that means that I'll get outcome 0 with probability 1, and I'll
Hmm.
get outcome 1 with probability 0.
Hmm.
Um, Whereas
And you'll
in
be able
the
to see
error
that.
case, I have the opposite thing. So here
And
I
you'll be
will
able to.
definitely get outcome 1, and I'll never see outcome 0.
And these scalar quantities are something you will be able to see classically at any time you want. Or what does it mean that you
So
do?
so this those scalar quantities are giving you the probabilities of the measurement outcomes.
Uh-huh.
So what I'll actually do physically is I'll do the measurement, and
Yes.
if I ran this experiment many times, then I would see the probabilities according to those scalars.
Okay. Okay. You do eventually have to measure this to see, but you call it detection. I guess I'm just wondering what that detection shows up as for the user of the quantum computer.
So the user will see just a bit. So they'll see the value of this bit k sort of come out. So if I do a single shot of this computation, it will just give me a measurement outcome. It'll give me a 0 or a 1 when I do this parity measurement.
Hmm. Okay.
Okay. Um, okay, so this is a very simple code. So it's in many ways it's analogous to what's called the 3-bit repetition code. So if I encode a single bit as 3 bits, and then I send those 3 bits to you, and you just look at the majority of those bits, then this is robust to any single bit flip, right? So if I encode 0 as 000, if any single bit gets flipped, you can still figure out that I wanted to send you 0, and similar for 1. So this is the quantum analog of that. But it can't handle any other kind of flip. So it can't handle Z flips, for instance. Those will go completely undetected, or rather, there's no stabilizer measurements which I could use to detect those. But if I look at slightly more elaborate codes, there are ways that I can detect all kinds of quantum errors. Okay, so the one of the simplest ones is this one called the Steam code. So here's a ZX diagram, which is picturing its encoder. Um, it looks fairly elaborate, but if you stare at this for a minute, you'll see that I've drawn a cube here in the middle with the vertices in alternating colors. And then my input is just connecting to one of the 8 vertices, and my outputs are just all the other 8 vertices. Okay, so one of those becomes my input, and the other 7 become my outputs. And this is what's called the Steam code. And this can correct any single qubit X, Y, or Z error. Or put another way, there's enough measurements which won't disturb um, a state encoded this way that I can, from those measurements, I can detect and actually correct any single qubit error. Okay, so this is almost the smallest example. There's actually a 5-qubit code, but its picture is a little more elaborate. Okay, so this is a huge area, quantum error correction, fault-tolerant quantum computing. And people doing ZX in this area is just like a tiny, but I would say growing, but a tiny little slice of what's going on here. And there's a few kind of main problems in this area that a lot of brain power has been spent on. Um, and I guess one of the most fundamental problems is constructing good codes. And especially of interest are good codes with a capital G, which is something that's been a kind of a hot topic in the last few years. So a quantum error correcting code, like a classical code, can be described by 3 parameters. So the number n is the number of physical qubits, okay? And we always want that to be small, right? Because that makes my code very efficient if I don't have to use too many physical qubits. K is the number of logical qubits, and we want that to be big for the same reason we want n to be small. Okay, we want to be able to encode lots of quantum data in not so much physical qubits. And the other thing is the code distance. So this thing measures the ability to detect and correct errors. Okay, so the distance is the size, or it's sometimes called the weight, of the smallest undetectable error. Okay, so that's how many single errors have to occur before I can't detect it using these stabilizer measurements. A very popular code family. So this is the one that, for instance, Google uses for everything, and their big results about fault tolerance last year was all in the surface code. Is called the surface code. Um, and it's nice because it's well understood and it has many advantages. So it has what's called a very good threshold. But its parameters aren't great. So for one thing, it always encodes a single qubit. So you can imagine like this big surface of physical qubits, but they always encode just one logical qubit. And the distance is square root of n. So where n is the physical qubits. That's pretty good, but you could hope for better. In particular, if I want to be able to detect up to 9 errors, then I need 10 squared. So I need n to be 100, right? On the other hand, kind of at the other extreme are what are called good LDPC codes. So this is like good with a capital G. It's a kind of a technical term. Um, and these things have great parameters. So both the number of logical qubits and the distance are linear in the number of physical qubits, which just seems like magic still. Um, but they're less well understood. So there's many things that people are just starting to figure out how to solve the decoding problem for these. They're a lot harder to implement in hardware, a lot harder to figure out how to do computation in. So there's many complications in working with these things. Um, and there's lots and lots more. So just like there's a complexity zoo, there's this really nice web page called the Error Correction Zoo, which you'll just find thousands of error correcting codes and their properties there. So I just wanted to point to a couple of ways that people have been using ZX to attack this problem. So one nice application is you can look at various normal forms of ZX diagrams, and these can give you canonical forms for encoders. And this gives you a good way to enumerate codes for, say, machine search, or count how many codes there are with specific parameters, or start to think about decoding errors in codes and that sort of thing. So here's a couple of refs for that. As you know, the slides are linked for all these refs. Other kinds of code constructions. So for example, you can have concatenated codes, which is where I take my qubit and I encode it in some physical qubits, and then I encode each of those into another code. And you can sort of figure out the result of doing that. So these are concatenated graph codes. Code transformations. So this is where I can sort of take codes and kind of decompose them into their pieces, so this is two transformations called code morphing and gauge fixing, which you can look at visually in ZX. Um, but yeah, I guess the main thing that I wanted to talk about, and maybe this is the thing I'm most excited about because this is kind of fresh off the press, is thinking about ZX for fault-tolerant quantum computing. And particularly this problem of compiling circuits with good fault-tolerant properties. So a big problem, even after you have a good error-correcting code, is you need to figure out how you can perform computations and measurements on that encoded data without ruining everything. Okay, so if I'm not smart about what I do to my physical qubits, I can actually end up spreading errors all over the place, and I've basically ruined my error-correcting code. So doing this in a smart way is called fault-tolerant quantum computing. And compiling circuits that work in this fault-tolerant way is a very hard problem. Okay, so I want to try to give you an idea of how this is difficult, and I can show you where things can go wrong. So say I have an error correcting code and I want to do these parity measurements. Okay, so on most hardware, this isn't a basic operation. So a superconducting, quantum circuit doesn't know how to do a 4-qubit parity measurement. I need to decompose this into more basic operations. So a natural question is, how am I going to implement this in terms of the gates and the basic measurements that I know how to do? So ZX can help with this. Um, And in fact, this is a kind of a standard calculation, but it looks very beautiful in ZX. Um, all I really have to do is I take this little dot that's connected to everything and I pull it down and I start to unfuse some spiders like this. And now I have an interpretation for this in terms of basic operations. So what did I do? I had my 4 data qubits. I bring in an extra qubit, which is called an ancilla qubit, and then I apply gates 4 gates onto the ancilla, and then I measure out that ancilla. Okay, so I might have written the other half of the trajectory here, but it doesn't actually matter because I don't care about the ancilla anymore. Okay, and you can see that this thing will actually fuse. If I fuse all the dots of the same color, it equals this thing on the left. Okay, so it's a very easy proof that those two things are semantically equivalent to each other. Okay, but then you can ask, is the left-hand side really equivalent to the right-hand side? And this answer is like that famous caveat. It depends on what your definition of is, right? So here it depends on what you mean by equivalent. Okay, so these things are semantically equivalent, and that if I took this thing on the left and I compute the linear map, then it's going to give me the exact same thing as the thing on the right because ZX calculus is sound, right? It can't help it but give me the same map. Okay, so both of these things give me the same linear map, which I can interpret this to mean that they behave the same way in the absence of errors. Okay, so if I had this sort of idealized measurement, this parity measurement, or if I had this implementation, in the absence of errors, these are going to do the same thing to my quantum state. Okay, but because these are decomposed into different basic gates, they can behave differently in the presence of errors. Okay, so an example of that is, suppose on this ancilla qubit down here, say halfway through, say this ancilla qubit got an error on it, and say I got one of these Z flips, or one of these green pi errors. Well, that's actually a bad thing for this circuit, because again, using ZX rules, I can see that this pi will copy through this red dot, and then this pi will copy through this red dot. and then it will sort of go away into this measurement. And what's effectively happened is this single error on my ancilla has come out as two errors on my data. Okay. So this doesn't really have the same behavior as my idealized measurement, because here over here a single qubit error can actually create two qubit errors. Okay, and that's bad. So if I am in a code that can only correct single qubit errors, then I perform this measurement, then I might have created an uncorrectable error in this way, even though it was still only a one qubit error. Okay, so the solution for this is we need actually a finer grained notion of equivalence. Okay, so here's you know for the mathematicians in the audience, a proper formal definition. Two circuits or ZX diagrams are called fault equivalent, which I'll write as this little equals with a hat. If for any undetectable fault, so I didn't really talk much about detection, but let me just continue. For any undetectable fault of weight W, okay, so the weight is the number of basic faults. Any undetectable fault of weight W on C, there exists an undetectable fault F prime of weight less than or equal W on D, such that C with this fault on it is equal to D with this fault on it, and vice versa. Okay, so this is, yeah, this is a little bit technical, but basically what this fault equivalence is saying is that there's a way that I can put the faults on the left-hand side in correspondence with the faults on the right-hand side in such a way that the faults are the same size. Okay, so I don't have this situation where I have, say, a single qubit fault on the one hand, which turns into a two qubit fault on the other hand. Okay, so this fault equivalence rules out those kinds of situations. Okay, and now this is a finer grained kind of equivalence. So while all the ZX rules preserve equivalence of the linear maps, only some rules are going to preserve this stricter thing, this fault equivalence thing. Okay, so you have to be actually quite careful in trying to figure out which ZX rules preserve fault equivalence. But actually, it turns out that we can find a few of these rules. And those rules are very useful for compiling fault-tolerant circuits. Okay, so it's no longer the case the generic spider fusion rule is a preserves fault equivalence. But this one where I sort of unfuse a one-legged spider, that one does. And this one where I take four-legged spiders and I unfuse it as a square like this, that also preserves fault equivalence. And there's kind of variations on these. And you can use these. You can use these to compile fault-tolerant circuits. Okay, so this gives a kind of a paradigm. Let's use that. Yeah, there we go. Which we've been calling fault tolerance by construction. Okay, so the idea is that you start with some idealized computation. So now this is built out of kind of ideal components that you may not know how to implement on hardware. So for instance, these high degree parity measurements. And you refine it with these fault equivalent rewrites until it's implementable on hardware. And what you know as a result of this is that your implementable computation has the same behavior with respect to faults as the idealized one. Okay, so I've taken a specification, I've refined it into something I can do in a provably correct way. Okay, so here's an example of one. So here's that 4-qubit measurement. This is just kind of circuit notation for it. And here I've done these kind of fault equivalent rewrites. And what comes out is a better version of that circuit. So the one that went wrong before, this is a better version. I instead of having one ancilla and doing C-naughts onto it, here I've prepared some entangled state, and I've done C-naughts onto each of the legs of that entangled state. And because I've done rules that preserve fault equivalence, I know that this is just as good as the idealized thing that I started with. Okay, and this picture is actually a known thing. So this is what's called Shor-style syndrome extraction. So named after Peter Shor of factoring fame. This is a way of doing fault-tolerant syndrome extraction. But something that's really cool about the ZX-based approach is now it's very easy to construct variations on this. So for instance, here I've got this four-legged spider. If I just kind of bend it around, if I bend a couple of these legs around, now I've got a spider with two legs in and two legs out, which I can figure out. Okay, I haven't given you the lemma, but I can figure out how to implement that as a little measurement gadget. And now I've done a fault-tolerant syndrome extraction circuit, and in fact I've used, well, it looks like two fewer, but actually this one uses an extra qubit. I've used one fewer ancilla qubits. Okay, so I've just by bending my diagrams around, I've managed to save some memory on one of these circuits, and nobody's ever come up with this syndrome extraction circuit before, so this is a new thing. And we've come up with families of these things which have better asymptotic behavior in certain situations, and there's a lot more we can do with these things. Okay, so I think this is very cool, and it's a very good way to work in a kind of a provably sound way with fault tolerance. Okay, so there's a lot of things that we're working on now, which kind of follow on from this. So that paper on the last slide is really just building the framework for this. And the kinds of things we're thinking about now are, well, just using it. So constructing cool fault-tolerant circuits this way. Perhaps more interestingly, thinking about trying to automate this compilation. Okay, so we know how to do this without fault equivalence in physics and quizzics and whatnot. So we're thinking of trying to come up with some interesting heuristics there, maybe using some ML or heuristic search type things. Automated checking of fault equivalence. So if I give you two ZX diagrams, can you check if those things are equivalent? This is going to be exponential. This is basically as hard as decoding for generic diagrams, but there's places where you can take shortcuts. Also thinking about rewrites that preserve efficient decodability. So decoding errors from syndromes is a hard problem. So if I have a code which can solve this efficiently, I kind of want to keep that when I do these kinds of rewrites. And completeness. So we know tons of completeness theorems about ZX, but we know almost nothing about this fault-tolerant ZX. So that's kind of those are kind of the big areas that we want to push this now. I figured in the last few minutes here, couple of minutes, I'd be a bit remiss to not kind of talk about a lot of the other stuff that's going on. So if you go on the website, you'll see that there's about 30 papers about ZX and quantum computing in the past few years. So I just wanted to point to a couple of highlights. This will be quite quick, but of course you can go check out the links on the slides. So one thing is these diagrams give you a good way to think about lattice surgery, which is a very popular way of doing fault-tolerant multi-qubit operations. The kind of time-independent nature of ZX diagrams is quite useful for relating different kinds of fault-tolerant paradigms to each other. So I can take a diagram and I can read time in different directions, and I'll actually see different ways to implement the same kind of computation. These kind of ideas have been pushed quite far by PsiQuantum, which is one of the biggest sort of quantum technology companies based in the US. So they have a whole paradigm, which is called active volume, which is really based on ZX calculus for doing fault-tolerant computation with photons. And yeah, I think this is this is almost the last thing, was flokeification. So this is this idea that if I have one of these kind of standard error correcting codes, I can turn it into this much more exotic thing called a flokei code, where kind of your code space is changing all the time, because anyway, I won't go into detail about that, but you can transform these regular codes into Floquet codes, which are more efficient in some ways, but still save the properties of the original code. And lots of other stuff. So higher dimensional systems, XYZ codes, GNON codes, a bunch of things. So yeah, well, it's exactly 650, so that worked out pretty well. I'll leave this last slide up. So here's the link to the free book. Please have a look at it. If you have any feedback, leave it as issues on the GitHub repository. And check out zxcalculus.com. Join our Discord. Come to our seminars. We're very friendly, and we'd love to have you. So thanks.
Great. Thank you, Alex. Okay. So if anyone has a question, feel free to raise your hand with the React button or just unmute yourself or type it in the chat if you prefer. Let's see. It looks like Kevin has a question. So Kevin.
Thanks for the talk, Alex. Let me know if you can't hear me on the move here.
I can hear you.
Great. So kind of a little bit of a meta question. I know you've got, as you said, these completeness results for ZX calculus itself, but there's work to do on understanding how complete ZX reasoning is for error correcting problems. So there's there's these theorem type questions about using ZX, but also just sociologically or in terms of covering the ground of everything that people in the field want to understand about error correcting codes. I guess the question I want to ask is something like, is there a substantial area, is there a chunk of this ground that you're pretty sure you can't cover with ZX if everyone would just convert to spiders?
That's a good question. I guess I would say probably no, because I don't anymore see it as a kind of an either or situation. So it's not kind of like you need to do ZX or you need to do things in the normal way. It's just another tool in your tool belt. And it seems like ZX has things to say about kind of all the main problems in terms of code construction, constructing fault-tolerant gates, constructing fault-tolerant measurements, and decoding problems. Uh, Maybe more speculative, that last thing, because decoding is something that sort of goes way back even into classical error correction, and but that's something that we're starting to think about as well.
Cool, that's helpful context.
Thanks, Kevin. Any other questions? Just to check, it wasn't obvious to me that your what you called equivalent fault tolerance equivalence or something wasn't equivalence relation, but it is one. Is that right?
Yeah, it is. So it's I just put as an abbreviation and vice versa. That meant kind of
Oh, okay.
that the symmetric version of this condition
Yes,
should hold as well.
I see. I was having symmetry problems. Great. And yeah, okay.
So I think it makes sense to think about a directed version where you're transforming things which never have worse behavior with respect to faults.
Mm-hmm.
But for
That'd
now
be
we're
like a
kind of thinking
rewrite
about
rewrite
equivalence. Somehow
system.
that seems easier to think about.
Mm-hmm. But that would be more like a rewrite system where less than or
Yeah.
equal to, you do a rewrite when it's good to do it.
Yeah. Yeah.
Okay. I'm not seeing any more questions, so let's give people another 30 seconds, but if no one interrupts me as I am speaking these last words, then I think what we'll do is we'll turn off the live stream and we'll stop the recording, and then we'll ask any last questions if people have them. But thanks again, Alex, for your talk, and
Yeah, thank you.
we'll put the slides online soon. And let me go turn off that live stream. Let's see, end stream.
Thanks, everyone.
Okay.